So that's ether gets protonated. This activates both electrophilic carbon due to greater positive charge onto electrophilic carbon, and you're gonna have better the leaving group. Okay, better leaving group. Here's better leaving group. Here also better leaving group. And this concept will be important for later, the reaction of epoxide as well. So the cleavage of cyclic ethers can happen in a similar manner. Like this is THF, 5-membered cyclic ether react with HI, heat to 150. If you use excess amount of HI, hydrogen iodide, you'll be getting, 1,5, the 1,4 diiodobutane. Okay, and the mechanism pretty much the same. In the first step, the HI is a very strong acid, and the ether molecule, the oxygen atom, is the most basic and the most nucleophilic one. So this is the base, this acid. So it's a proton transfer reaction. You will get a protonated ether. And the protonation of ether have two important consequences. First, it increases the amount of positive charge on these two carbons, because the protonation makes the oxygen more electron hungry, so the positive charge of this carbon increases. Second, you are having a better leaving group. So if you think about this bond breaks, then this part is a neutral alcohol, is a many orders of magnitude, the better leaving group than the alkoxide. So that basically readies up these two carbons for SN2 reaction. And at the same time, iodide, just like bromide, chloride, they are extremely good leaving groups. So you will nucleophilic attack this electrophilic carbon, while this part of the molecule serve as a leaving group, give you the iodo alcohol. And this is one of slow steps. This is SN2, because of nucleophile attacks here. At the same time, the bond to leaving group breaks is SN2. Okay, and then this alcohol functional group react with another HI. This another SN2 reaction give you another iodide. Okay? So the mechanism, this step I will not repeat it, but we have discussed extensively in organic 1 as early as chapter 5. Now, the interesting thing is whether you have if ether is LQ arrow ether, means the two hydrocarbon group, one is aromatic, one is LQ. Okay, if this kind of ether are allowed to react with hydrogen iodide, and you are not, even you're using excess amount of hydrogen, the hydrogen halide, you use excess amount of hydrogen halide, you will only getting one, you're only getting one bromide, one halide as LQ halide, and the aromatic part, they will, be convert to phenol. Okay? So the why that's the case is because of in the aromatic ether, aromatic and the LQ ether, these two carbon oxygen bonds, they are different. Okay? This carbon oxygen bond is between a sp2 hybridized carbon and oxygen. Okay? And this carbon oxygen bond is between an sp3 hybridized carbon and oxygen. So this bond, these two bonds are of different strength. So let's say, just using one example here. So if you have this guy, ethoxybenzene, if we treat excess amount of HBr, okay, so what will be happen? Okay, so first thing, you probably can guess what will be happening. Can anyone tell me? We already discussed the other ethers. What is the first thing will be happening? protonation, very good. Thank you, Nadia. So this protonation, because ether oxygen is the most nucleophilic atom because of it has high concentrated negative charge due to having two lone pairs only. Okay, and the HBr is a strong acid, so this is very fast proton exchange reaction. So lead to a protonated ether. And this protonation still give you the same effect we have seen earlier. So it increases the positive charge on these two carbons, okay? These two carbons, okay? Because of protonation makes oxygen more electron hungry, so increase positive charge, okay? And also, the makes the two potential leaving groups, like this one, will be the leaving group if you consider this one is electrophilic carbon, okay? Or if you consider this one, okay, is electrophilic carbon, then this thing will be leaving group. In both cases, you are getting the good neutral leaving group. Okay? Now the question is, these two carbon oxygen bonds are different because of this carbon oxygen bond. Okay, is a sp2 carbon oxygen bond. This carbon oxygen bond is sp3 carbon oxygen bond. So the left side bond is stronger. Right side bond is weaker. So this alone can justify why nucleophile, here is the bromide, okay? You are getting the bromide. Nucleophile will attack this carbon, not this carbon. Okay? This alone can justify, but we have more to say. Okay? Okay, let me rewrite it, maybe easier. So because of this carbon oxygen bond is weaker than carbon oxygen bond. So breaking of this carbon oxygen bond is easier than breaking of this carbon oxygen bond. Okay? So this alone can justify, okay, this nucleophile can attack here and give you this one. Okay? Then this will give you the ethyl bromide plus phenol. The other reason, for bromide not attacking this one, okay, is because what kind of attack will be if bromide directly attack this carbon before this carbon oxygen bond breaks? What's the mechanism? If this bromide were to attack this carbon before this carbon oxygen bond breaks, this attack would be what? SN1 or SN2? This attack this carbon before this carbon oxygen bond breaks. This would be SN1 or SN2? One? No, SN1 is a leaving group break first to give you carbocation. That's a unimolecular reaction. See if you have this one, okay, react with HBr, okay. The first step is the protonation. That's not a rate limiting step, okay. SN1 is this one breaks, okay, give you carbocation. This rate limiting step, and if why this called SN1? Because this rate limiting step and only has a single reactant we call SN1. Okay, so SN1 always the leaving group leaves first. nucleophile come next. This is called SN1. So if this bromide attack here, before this one breaks, this would be SN2. And SN2, the nucleophile always attack the electrophilic carbon from the opposite side of the leaving group. And can the nucleophile approach this carbon from opposite side of leaving group? This is a leaving group. And opposite side of leaving group is a ring. And the nucleophile cannot come to this carbon because of this blocked by the ring. Okay, so SN2 is impossible. Okay, to attack this carbon. What about SN1? If it's SN1, okay, you have to say you have phenol. If you to react with, if you think a phenol, okay, phenol, yes, it can react with HBr, give you the protonation product. That's possible, okay. But the reaction we're gonna stop there and this equilibrium process, okay, because we know that SN2 won't really happen because of the the leaving group. There's a nucleophile cannot access this electrophilic carbon because if you would like to access the electrophilic carbon must be from the opposite side of leaving group. This is the leaving group. This is the leaving group. Okay, opposite side of leaving group is the ring. So the nucleophile cannot approach the electrophilic carbon through the ring. You can't. Physically impossible. Now, what about SN1? If it's SN1, you need this one to become carbocation. Okay. And this phenylcarbocation is very unstable. For the same reason, I explained it in Organic 1, Chapter 9. Okay, for the same reason why this one, the vinyl cation is very unstable. Okay, for the same reason. Okay, and actually the phenylcarbocation will be even less stable than regular vinyl carbocation because of the if you have vinyl carbocation, as we show in here, what would be the hybridization state of this carbon? What is the hybridization state? So think about, okay, if this one, what is the hybridization state of this carbon? For this one, regular alkyl carbocation. This carbon, what's the hybridization state? What? It's kind of disappointing. Nobody knows what is hybridization of this carbon. Well, I really shouldn't give you guys any extra credit if that's the case. If nobody can know this one, hybridization of this carbon. Yes?
It's sp3.
This one? sp3 is if it's neutral, let's say, isobutane, okay? This carbon is sp3, okay? Just regular alkyl carbon, sp3. But this one is a positive charge. It really is kind of disappointing. This is a central topic in organic work. If nobody knows, really, I'm really gonna have a hard time to justify give you guys anything extra in terms of credit. Okay, you all forgot. Okay, it's kind of very disappointing. Anyway, so the carbon positive charged carbon in alkyl carbocation is sp2. So if it's a vinyl one, it will be sp hybridized. If it's sp hybridized, it would be linear. Okay, but if it's a phenylcarbocation, this also is sp hybridized. and then its angle strength will be extraordinarily large because we know it's part of ring. Okay, you will have a hard time to get in S 180 degree. So this is very unstable carbocation. That's why SN1 also will not work. Okay, so that's the reason why the if you have aromatic and the LQ ether, the bromide will only be connected to the sp3 hybridized carbon, not the not this carbon, because the first when it's the ether is protonated, the nucleophile will only react with this carbon because of this carbon oxygen bond is weaker than this carbon oxygen bond, so it's easier to break this carbon oxygen bond, and will be getting will give you a LQ halide and a phenol. And the phenol will not react with hydrogen, will not react with further with hydrogen halide because first, as yes, a phenol could be reversibly protonated, but the reaction will stop there because of the protonated phenol will not be able to undergo SN2 because of the opposite side of Levy group is not accessible, and also will not undergo SN1 because the formation of carbocation is extremely difficult. Okay? So the rate will be exceedingly slow. So as a result, if you have aromatic and LQ ether, it reacts with excess amount of hydrogen halide, you will only getting aromatic halide. So let's say like this one, if we react with HI excess, and you will only getting the aromatic part will be obtained as the phenol form, and the LQ part will get in the form of LQ halide. Okay, so that's the difference between di-LQ ether and aromatic LQ ether. Here's just another example. So this whole thing, okay, is aromatic group, and this part is LQ group. So you will be getting the for the aromatic group, you will be getting as in the form of phenol. So this whole thing, okay, is the aromatic. I'm sorry. I think I should the exclude the oxygen atom. So this one is aromatic group. Okay. So it will cleave off in the form of so this originally connect to O, but it had another OH. So that's how you get the phenol. And the LQ part will be cleaved into LQ halide. Okay. So that basically the regular ethers. We're only going to talk about this single reaction, the cleavage by hydrogen halide. And then let's talk a little bit of preparation of a special kind of ether called epoxide. And before we talk about reactions of epoxide, and the reaction of epoxide is actually one of the focal point of this chapter. So we actually already learned the kind of method by which we could prepare epoxide from organic one. That's that's the method 2 mentioned here. Basically, we're using oxidant to establish both carbon-oxygen bond at once across the carbon-carbon pi bond. That's the epoxidation reaction we learn in organic one. So you will need alkene to react with the peroxy acid. That's that's only reaction we have learned so far by which we can get epoxide. But here, we also learn another method. So basically, we're going to install alcohol oxygen 2 bonds away from an electrophilic carbon. Then we perform intramolecular SN2. So actually the both methods, will start from alkene CC double bond. The difference is the method 1 requires 1 step, but the method 2 requires only, method 1 requires 2 steps. Right? Method 2 requires only 1 step. But the difference in the peroxy acid is not a super stable compound. And if you don't have access to peroxy acid, and then the method 1 might be a better option. So for both methods, the pi bond must be a good nucleophile. So what does that mean? Means this method, these 2 methods will not work well on unsubstituted CC double bond. In the let's say just plain ethene. Okay, so this CC double bond has substantially lower electron density than something like here. Okay, again, this is something we learn in organic 1. Alkene nucleophilicity depends on the pi electron density, and because if you compare alkenes with different degree of substitution, and CC double bond has more alkyl groups attached to it, the electron density on the double bond will be higher because each alkyl group is sp3 hybridized carbon, and the double bonded carbon, they are sp2 hybridized. And as we know, and as you should know at least, sp3 hybridized carbon has a lower electron activity than sp2 hybridized carbon. So each such alkyl substitution will donate some electron density to the double bond due to this inductive effect. So the more alkyl groups you have on the double bond, the electron density on the double bond will be higher. And then when the electron density on the double bond is higher, it's more nucleophilic. So that's something we learn in organic 1. Okay. So in both reaction, both method, preparation method, the alkene double bonds, they are acting as a nucleophile. So we wanted if we wanted the reaction to work well, the pi bond must be reasonably nucleophilic. So this is a reaction we learned in organic 1. So you have a CC double bond and react with a compound called peroxy acid compared to regular carboxylic acid. You have an extra oxygen. Okay? So this oxygen-oxygen single bond is weak and more highly polarizable. So that's why this oxygen atom could be a good, could be electrophilic. It can react with CC double bond. This reaction rate is only depends on the pi electron density on the CC double bond. So this is a single-step reaction, Singh addition. So what does it mean, Singh addition? Is if you have that means that 2 CO bonds form at the same time. So under that means the bond rotation will not be possible. So if you have this one react, if you have a trans, the alkene, you will get the trans epoxide. So let's say, maybe we should say, something like that. Okay? This is called Singh addition, trans epoxide. Okay? If it's cis alkene, you get a cis epoxide. And the you want this as I said, the proxy acid is electrophile and the alkene is a nucleophile. So you don't really want to using alkene without any alkyl group to do this reaction. And and if you recall what we learned in organic one, the reaction rate is directly related to the number of alkyl bonds on the double bond. The more alkyl groups on the double bond, the reaction will be faster. And the second, the other method, two-step method, first involve the vicinal halohydrin formation reaction. Again, that's a reaction we learned in organic 1 in chapter 8, I believe. So the alkene is first react with a halogen, usually chlorine or bromine, not iodine, not fluorine. Fluorine is overly reactive, hard to control, or may cause explosion. Iodine is too unreactive. So bromine, chlorine are typically used in aqueous environment. This gives you vicinal halohydrin, the product. And this reaction, is anti-addition and follows the Markovnikov rule. And if you forgot what this means, please revisit chapter 8, the organic 1. I will not go through the entire process again. But very quickly, if you want to know the essential mechanism, it will be like let's say if using one alkene as the example, like here, and the bromine and the water. Okay, so this one, okay, the alkene will be acting as a nucleophile, attack the bromine, and the give you the bromonium ion, as the intermediate. Okay, and then the bromonium ion. This is a rate limiting step. Okay, then the bromonium ion will react with the most abundant nucleophile in this reaction system. And it's important that although this reaction is SN2 in this step, okay, but the water nucleophile will be attacking the more substituted carbon. And that is because this reaction involves in the transition state, okay, and which is cationic. Okay. So it's SN2. So at the transition state, the water molecule, say here, nucleophile, okay, and because we know it's SN2, so the water will be donated its lone pair, okay, to this electrophilic carbon, and then this one will break, okay, and at the transition state, the oxygen will be partial bound to this carbon, and this carbon-bromine bond will be partially broken. So what you will be seeing in the transition state, you will have something like water partially bound to this carbon, then this carbon is partially bound to bromine, and this carbon still will bond to the 3 other carbons. This is part of the ring, 6-member ring. So if you look at this kind of transition state, because of the water partially donates the lone pair to the electrophilic carbon, So water going to carry a partial positive charge. And because of this bond is halfly broken, so the bromine no longer have the whole unit positive charge, will only carry a partial positive charge. For the same reason, this central carbon also carries a partial positive charge. Okay, so this is a transition state. Okay, transition state. This transition state has a carbocation character because of this carbon is a positive charge. So this transition state has a partial carbocation character. Okay. So what does that mean? So the its stability is impacted by structure in the same way as carbocation. And as we know, carbocation, its stability increase with the degree of alkylation. So tertiary is more stable, secondary is okay, primary generally too stable to form. Okay? So now if the water attacks here, you get this transition state. It's like tertiary carbocation. Okay? And now if water reacts with I'm emphasizing this because later we're going to see similar situation in the epoxide reaction. Okay, so if water reacts with this guy, and that transition state will be different. Okay, that transition state will be, let me draw it here. So this is if the water attacks the less substitute carbon. Okay, it will be this is the other transition state, blue transition state. So because of these two transition states, they have a carbocation character. So we can see the black transition state, due to higher degree substitution at this carbon, is more stable than the blue transition state. So if the black transition state is more stable, then it will have lower activation energy. So the nucleophile, the black pathway will be faster than the blue pathway. Okay, so that's why the eventually you are getting the black pathway give you what product? Give you the let me switch to black. I don't want to use color in confusing manner. So you will get this one. Okay, so this vicinal hydrogen, the OH will connect to more substitute carbon, and because of the OH, the water react with this one is SN2 type of reaction, you have configuration inversion. So the hydroxy group always is anti to the halogen. Okay, so that's the reaction. You have learned organic one. I'm just refreshing it. Okay, and now if you treat this guy with a hydroxy group, and what happens is first the hydroxy group will remove this proton, and this hydroxy group. I'm sorry, it's treated with hydroxide ion, the sodium hydroxide or potassium hydroxide ion. You will be easily remove a proton from this hydroxy group. And this hydroxy group is more acidic than regular alcohol. Why? Can anyone tell me why this hydroxy group is more acidic than regular alcohol? Think about the basic principle about the structural acidity correlation we learned in Organic 1, Chapter 1. So what structural feature can enhance the acidity of this hydroxy group? Assume this X is, say, bromine, chlorine is the most common one, okay? So how do you explain this hydroxy group is more acidic than regular alcohol hydroxy group? No one knows? Okay, or no one want to talk? That's why I repeat it again. I really want to see the next class. I see a bit more response from this class. Just give me some motivation to give you some more extra opportunities. If you guys don't give me motivation, it will be very hard for me to give you more extra opportunities. Okay? Yeah.
Is the halogen making a positive more nucleophilic?
If halogen makes something more positive, would it be more nucleophilic? I mean, yeah, halogen, yes, can make something more positive because halogen are generally electronegative, right? But it makes make it more positive, make it more nucleophilic, seems not a normal correlation. Because it's you have this halogen, right? Should make this carbon more electron positive. It's make it more electrophilic, not a nucleophilic, right? Yes, focal point is a halogen, but how can they increase the acidity of this hydroxy group?